Welcome to G Fun Facts Online. Look around you right now. How many charging cables can you see? For your phone, your laptop, your watch, your headphones. Our modern world runs on electricity, but it's shackled by copper wires. But what if those wires could just disappear? Not just the charging cables on your desk, but all of them. Imagine a drone that never needs to land to recharge. A medical implant inside a human body that runs forever without replacement surgery. Or even a microchip, 1,000 times more powerful than today's, powered not by a tiny, fragile web of wires, but by light itself. This isn't science fiction. This is the story of how the wires that have bound us for a century are beginning to dissolve, and how a new light is dawning on silicon. For decades, wireless technology has meant data, Wi-Fi, Bluetooth, 5G. But the final frontier has always been power, the dream of cutting the last cord. We're now finally on the cusp of that reality, and it's happening at two extreme scales, from beaming power across entire landscapes, down to the unimaginably small world inside a processor. Let's start with the big picture. In a recent groundbreaking experiment, the US Defense Agency, DARPA, did something straight out of a sci-fi movie. They successfully transmitted a significant amount of power wirelessly over a distance of more than 5 miles. The project, called POWER for Persistent Optical Wireless Energy Relay, uses a highly focused beam of laser light to send energy from a transmitter to a receiver. At the receiving end, a specialized photovoltaic panel, similar to a solar panel but tuned specifically to the laser's frequency, converts that light back into direct current electricity with incredible efficiency. So what did they do with this beamed power? To prove it worked, they did something brilliantly simple. They made popcorn. It's a whimsical demonstration, but the implications are profound. Imagine disaster zones where the power grid is down. First responders could fly in a transmitter and beam power directly to hospitals and communication centers. Think of military applications, where forward operating bases in remote locations could be powered safely from a distance, without the need for vulnerable fuel convoys. Or consider fleets of electric drones, able to stay airborne indefinitely, creating a persistent eye in the sky for things like monitoring wildfires or agricultural fields. They would simply fly into a charging beam when needed, like a car pulling into a gas station, but without ever touching the ground. Of course, there are challenges. The beam needs a clear line of sight, and things like clouds or heavy rain can interfere with it. And yes, safety is a major concern. You wouldn't want to accidentally fly a kite through a multi-kilowatt laser beam, but the proof of concept is there. Long-range, meaningful wireless power transfer is no longer a theoretical dream. But as amazing as that is, perhaps the most impactful wireless power revolution is happening at the opposite end of the scale. It's happening inside the very silicon chips that power our entire digital world. To understand this, you need to know about a hidden crisis in computing. Inside every microchip, there's a complex, microscopic network of copper wiring called the Power Delivery Network, or PDN. Its job is to deliver the precise voltage and current to billions of transistors. Think of it as the chip's circulatory system. For the last 50 years, as we've made transistors smaller and smaller, we've also had to shrink this wiring network. We're now at a point where this network is becoming a fundamental bottleneck. The wires themselves take up valuable space that could be used for more transistors, they generate heat, and they cause voltage drops, which is like a drop in blood pressure for the chip, leading to errors and limiting performance. This is the power wall. We can't simply make chips faster just by shrinking transistors anymore. We're hitting the physical limits of how we can power them. The solution is to get rid of the wires. Two incredible technologies are leading this charge: backside power delivery and optical power delivery. Let's start with backside power delivery, or BSPDN. For decades, we've built chips like a single-level city, with the power lines and the data lines all crammed onto the same surface, fighting for space. BSPDN is like turning that city into a multi-level metropolis. Engineers are figuring out how to move the entire power delivery network to the back of the silicon wafer. This creates a complete separation, a clean, robust power grid on the back, and a super-fast, high-density data network on the front. It's like having dedicated underground tunnels for all the power cables, leaving the surface free for high-speed transit. This allows for more transistors, better performance, and a more stable power supply. Leading research institutes like IMEC in Belgium are already demonstrating that this approach can significantly boost chip performance. But the next step is even more radical: getting rid of the copper wires entirely and replacing them with light. This is optical power delivery. The concept is beautifully elegant and mirrors the large-scale DARPA project. An external laser shines light onto the chip. Then, integrated directly into the silicon, are microscopic photovoltaic cells, tiny solar panels, that convert that light into electricity right where it's needed, next to a block of transistors. This eliminates the sprawling, inefficient network of copper wires completely. The power arrives wirelessly, delivered by light. This not only solves the power wall problem, but also drastically reduces heat and electrical interference, allowing for the creation of incredibly dense, powerful, and efficient 3D stacked chips. We're talking about stacking multiple layers of processors and memory on top of each other, all powered by light from within. Now, let's connect the massive scale of laser-beamed power and the microscopic scale of on-chip light delivery. Where do they meet? They meet in a world filled with trillions of tiny smart devices. The Internet of Things, or IoT. We talk about smart homes, smart cities, wearable sensors. The biggest challenge for all of these devices is power. Batteries run out. Wires are impractical for a sensor embedded in a concrete bridge or a medical device in the human body. This has given rise to the concept of zero power or self-powered sensors. These are devices designed to run for years or even indefinitely without ever being plugged in or having their battery changed. They do this through energy harvesting. They scavenge tiny amounts of energy from their immediate environment. A sensor on a factory machine could be powered by the machine's own vibrations, using a piezoelectric material that generates a current when stressed. A remote weather station could be powered by the temperature difference between day and night, using a thermoelectric generator. And increasingly, they can be powered by harvesting ambient radio waves, the leftover energy from Wi-Fi, cellular, and broadcast signals that are all around us. When you combine this with ultra-low power electronics, you get a device that can sense its environment, perform a calculation, and send a tiny burst of data, all using only the energy it can pull from the air, from vibrations, or from stray heat. Imagine a world where every single object can be a smart object. Medical implants that monitor your vitals and are powered by your own body heat. Structural sensors inside buildings and bridges powered by traffic vibrations, warning of failures before they happen. Smart dust, tiny sensors that can be scattered to monitor environmental conditions, all powered by ambient light or radio waves. This is the ultimate expression of the wireless world. Not just cutting the cord to your phone, but eliminating the very concept of a power cord for a vast new ecosystem of technology. From making popcorn from 5 miles away with a laser to powering the next generation of supercomputers with internal light beams, we are fundamentally redefining our relationship with power. The tangled wires that have defined the electrical age are giving way to a more elegant, more integrated, and far more powerful future. A future powered by invisible forces and beams of light, seamlessly woven into the fabric of our world. A new light is truly dawning on silicon, and it's going to change everything.